The Node.js process object is a global entity that provides direct access to the current runtime environment. It acts as a bridge between your application code and the underlying operating system, allowing you to interact with the process lifecycle at any moment. You use process.version and process.arch to identify the specific Node.js release and the underlying CPU architecture. These properties ensure your application runs on compatible hardware and utilizes the correct feature set for your deployment environment. Performance tracking begins with process.uptime, which reports the exact number of seconds the current process has been running. This metric is essential for calculating availability and identifying long-running processes that may require a restart. To manage memory, process.memoryUsage provides a snapshot of the current heap allocation and resident set size. Monitoring these values allows you to detect memory leaks and optimize garbage collection before they impact application stability. Finally, process.env grants access to user-defined environment variables, which are critical for configuring applications across different deployment stages. Mastering these properties transforms your ability to debug, monitor, and scale Node.js applications with precision. We begin by checking for Node.js, but since it is not installed, we use the package manager to fetch it. By running an update followed by the install command, we pull the latest binaries from the repository. This ensures our environment is ready to execute JavaScript code directly from the terminal, which is essential for server-side development and automation tasks. We start by running node-v to check the version. The command not found error indicates that the Node.js binary is missing from our system's path. This confirms the shell cannot locate the executable, signaling that we must install the runtime environment before we can execute any JavaScript code. With the installation complete, the system now recognizes the node command. We are setting up a comprehensive diagnostic string that queries the runtime environment. This approach allows us to inspect internal process metadata, such as the current version, system architecture, and memory consumption, providing a clear window into how the Node engine interacts with our underlying operating system. The package manager is unpacking and configuring the Node.js dependencies. Notice the Update Alternatives utility, which maps the Node.js binary to the standard JS command. This ensures your shell correctly resolves the executable path, effectively integrating the runtime into your system's environment for immediate use.
Executing this chain of commands reveals the runtime state. We see the specific version, the CPU architecture, and the current memory heap usage. Finally, we print the system path variable to verify our environment configuration. These metrics are vital for debugging performance issues and ensuring that our applications have the correct access to system resources and environment variables.
The double ampersand operator chains these commands, ensuring each executes only if the previous one succeeds. By passing the nice E flag, we instruct Node to evaluate the provided string as JavaScript code, directly accessing the global process object to retrieve real-time metadata about our active runtime environment. The output displays the process memory usage as a structured object. The RSS field represents the resident set size, the portion of memory occupied by the process in RAM. Monitoring these values helps you understand how Node.js manages heap allocation and external memory resources during runtime execution.